At the heart of all ShapeGrabber systems is the scan head. ShapeGrabber has a family of scan heads designed to operate optimally for parts of different sizes. The scan head is composed of two main elements, the laser and the camera. The laser projects a light beam on a portion of the object being measured, and the camera detects the reflection of this laser beam from the surface of the object. It is important to understand that it is the diffuse reflection that ShapeGrabber uses to measure the distance to the object. Diffuse reflection is the reflection of light from an uneven or granular surface such that an instant ray is seemingly reflected at a number of angles. This is different from specular reflection, like that from a highly polished mirror where all light is reflected at the same angle. At a microscopic level, most surfaces have some level of granularity, so that incident light is usually reflected both diffusely and specularly. Because diffuse reflection goes off in all directions, some of the light will make its way into the camera. The angle at which the light enters the camera depends on the distance of the object. If we place a linear detector behind the camera with multiple pixels, different pixels will be illuminated depending on the incidence angle of the reflected light. If we know the exact relative positions of the laser and camera, then we can calculate the distance of the object. This is known as triangulation and has been used to calculate astronomical distances for thousands of years. But the ShapeGrabber scan head does not project a single point laser beam on the object. It actually shines a plane of light. Planar triangulation works the same way as single point triangulation, except that instead of a linear detector, we use an area detector. Think of the ShapeGrabber scan head as over 1,000 single-point triangular sensors placed one next to the other. The ShapeGrabber scan head, with one frame of the camera, takes the image of a complete profile of the part at a given height. The image of the profile is treated as over 1,000 individual points. The exact distance and position along the profile are measured through triangular and other more subtle methods and corrections for all of these sampled points on the profile. This gives us 2 of the 3 coordinates we need. By moving the scan head over the object being measured and acquiring profiles at different heights, we are able to get that third dimension. We build up the complete surface of the part, one profile at a time. If you know the scan head position and speed, as well as the frame rate of the camera, you can then build the complete surface dimensional map of the part. Any object is essentially composed of many individual points. If the point density is high enough, not only can individual dimensions be taken, but you can actually see what you are measuring. A ShapeGrabber scan has hundreds of thousands or millions of data points. Each scanner is characterized by its scan volume. The scan head can measure single profiles in a certain scan area in the shape of a trapezoid. The length of the trapezoid is the depth of field. The height of the trapezoid is the field of view, and it varies from a minimum value in the near field to a maximum value in the far field. The distance between the scan head and the start of the scan area is the standoff distance. So that when the scan head is moved, the scan area of the scan head becomes the scan volume of the scanner. The resulting scan volume is in the shape of a trapezoidal prism. Objects placed outside the scan volume will not be measured even if they are illuminated by the laser. The scan volume is limited by the requirement that each point being measured must be illuminated by the laser and visible to the camera simultaneously, and both of these elements have specific operating ranges. So now we understand the scan volume of a single-axis scanner. But what about the scan volume of an index scanner such as the AI310? This scanner has a rotary platter and linear motion parallel to the rotation axis. The scan volume will be a cylinder with diameter equal to the depth of field of the scan head and the height equal to the scan distance of the linear axis. On the AI810, the position of the rotary platter is variable, mostly to accommodate different scan heads. The platter is usually placed such that the center of the platter is in the center of the depth of field of the scan head being used. This is the case for the object being scanned in the left-hand image. However, by shifting the platter to the right, the AI810 can actually scan larger parts. This is shown in the right-hand image. The limitation is that some internal or inward-facing features of the part that are too far away from the scan head will not be digitized. For example, in this case, the inward face of the tall column on the right will not be measured, but when the part is rotated 180 degrees, the outside surface of the same column will be measured.